Alright, apologize for that. How's it going, everyone? And hopefully your Tuesday's going well. We're going to be working on the lightsaber some more today. Same bounties are still unclaimed, so they are all there. And let's just get back into this. So last time we made the model for the accelerometer. So this time I should be able to just make the footprint and the schematic symbol and everything. So let me pull that up real quick. All right. Still a couple things I need to pull up. I apologize for not having everything ready to go. The streaming software decided to just mess up right before I started, and had my microphone not working and just a whole bunch of other random technical difficulties. So combined with the Windows update and everything, it was just catastrophic. All right, but we're getting there. Okay, so here's our bill of materials. We need to add the let's see, not that 2809. Yeah, okay, that's what we need to add. Where is my I don't have my diagram pulled up. That's what I'm missing. Man, I am all over the place to start this. All right. So our two accelerometers, the Adafruit 2809, I'm going to pull those up. And this will get us started. Okay. So it's this thing right here. So we need to go through and do our pinouts for this whole thing and make this part. And I believe down here somewhere we have a, no, we have a spec sheet or something. Here we go. In this file we have our layout and everything, which is what we need. Okay. So let's get started. Parts. And then here we're going to look up Fruit 2809. If we're lucky, we'll be able to use something that's already been made before. Okay, unfortunately, this one does not have all of the pins, so that's disappointing. Let's go to Edit. Give it a sec. Oh, let me turn the music back on too. I just realized it's still off. All right, I don't know if this is going to display or not. There it goes. Okay, yeah, so this is an old version of the board, I think, which explains a lot. So we're going to have to modify this. So most of this that's here we can still use. So what is our... Yeah, this is definitely the old version of it. Okay, cool. At least that makes sense. Okay, let's see. If I get a better look at one of these, that would be helpful. Kind of. AC1, AC2, AC3. Okay. So I'm probably going to reorganize a lot of this then. Well, maybe not. Let's see. SDO, CS, SCL, SDA. It really just needs a bunch of extra ones added, and I could just throw those in up here. So I think I'm just going to do that, actually. One. Come on. 2, 3, 4. All right. So then VN is 1. 2 is 3 volt. Ground is 3. SCL is 4. SDA is 5. Interrupt is 6. Based off of this. CS is 7. SDO is 8. And then A1 is 9. A2 is 10. A11 is A3. And then I2 is 12, or interrupt 2, I think is what that is. Okay. So that should be everything from a schematic symbol standpoint. Let's save that. And then for the footprint, I guess we edit this too. Do we edit or add? Let's just add, just to be safe. Okay. So for this, we're going to need a lot of vias. Oh shoot, what is the diameter on these? I followed some standard and I don't remember what it is. Excuse me. Here, let me go look for the header that I found. That'll at least tell me. The hole is 0.9 millimeters. Okay. Let's go metric here. Okay. I'll make that a little bigger, and then there's not really much else we need to do other than name them and place them around. I think. Oh, actually, you know what? This one I picked may not be right. Let me find. Let's pick one with the appropriate pitch. Okay, the hole size is 1 millimeter, typically. Not just this random header that I've picked. Okay. And the distance is 2.54 apart. I might make the outer a little bigger. Let's make it like 1.7, just so we have more to solder to. That's better. All right. Then going off this drawing, all right, it might actually make sense in this instance to do inches. So y is going to be 0.25. And then the x is going to be hang on. I guess 0.05 because they're 0.1. That doesn't look right. Oh, this is in mils. I want this to be in inches. Okay, fine. I do 50 mils and 250 mils. Okay. Two, three, 4, 5, 6, 7, 8, 9, 10, 11. Negative 50 and 250. Negative 150 and 250. Negative 250 and 250. Whoops. All right, there we go. So that's the top row. And then this one, basically do the opposite of that on the y-axis. Negative, well, this is negative 250 as well. No. 50. Negative 250. Okay. All right, there we go. And now we need to rename them all from 11. So this is going to be 1, and we're just going to go around. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11's correct, and then 12. Awesome. Okay. Sorry. So now that's good. Let's add our model in here and then see how that does. So we're going to add a 3D body. I guess let's just go around. Okay. Generic, choose. Not that one. Hold on, I gotta find it. Okay, I think that's it. We hit OK. Interesting. Something seems off. Right, okay. Well, it could be worse. Yeah. Alright, there's no axis in here, so we do need to rotate it. I'm assuming rotate around the X. 90? Question mark? Let's start with that. Oh, that looks like it lines up better. Okay, it's upside down, but we're getting there. So let's make that 270. And then we'll probably have to move the height as well. Alright, we're closer. Oh, that's why I couldn't see the axis, because it was in the middle of the thing. So this should be lined up vertically. Okay, it is, I think. It looks like everything's inside is looking pretty good. Maybe. But I need to raise it up the right amount, and I don't know where that is. Let's try going up 1.5 millimeters. Alright, let's change the metric again. Alright, standoff height 1.5. Okay. Where does that put us? Not quite there. Let's go to 2. Really? That's not going to do it either? Alright, let's go to 3. There we go. It's not quite that high. Maybe 2.5 is enough then. Two 2.6 actually, for board thickness reasons. Okay, yeah, there's a little space there. That looks good actually. Alright, let's see how we're doing. Yep, the whole size seems right. Alright, cool. So that looks good. So now we need to do something for the mounting locations. Not that we're likely to use them, but I want to include them. I think this is really going to put in perspective too, compared to the other boards, like how small this is. Just checking out these different views that it offers. Interesting. Okay, let's go back to Imperial for our measurements. All right, the next one, we need mounting vias. Do these count as pads? Can we just say via? Have it unlabeled? That makes more sense, I think. Alright, diameter. I thought I set this to metric, I guess not. Oh no, I did set it to imperial. I wanted to do that. Whoops. Alright, there we go. 0.1, so 50 mil. We would want this to be 100 mil diameter. Oh, more than that actually. Maybe like 150. Because the hole needs to be 100 mil. Okay, there we go. And then offsets are 0.25 up and 0.4 over. There we go. All right, let's place a bunch around. Okay, so 400, 250. Negative 400, 250. Oh, shoot. Come back. Negative 400, negative 250. Negative 250. Okay. So now if I go to the three-dimensional view, we should be able to see that set up there. Yep. Oops. Looks good. I'm not sure those mounting points will ever be really useful, just because of how close they are, but maybe. I did the same diameter in the board as the upper one is, so that should be okay. Alright. That's good. Let's save that. I probably need to edit this one with these values in order for this to be correct, because I don't want this to be incorrect. I'm just thinking through that now. I think the only ones that are going to be correct are 7 and 8. So VN, 3 volt ground, SCI. VN, 3 volt ground, SCL actually. SDA, INT. SDA, INT. This should be INT. No, INT should be 8, so this should be 6. Okay. Then SDO and CS are what? SDO is 8, CS is 7. So 7 is correct. This needs to be 8. And making this change will allow this to stay consistent with the schematic. Even though it's weird out of order here, it's the same as the schematic symbol, which will be good. Okay. So now we need to save this to the server. Xenobite Offsec, thank you for the follow. Oh, validation error. No. Okay. No, don't release yet. Oh, missing footprints. That's fine. But what is this? Duplicate primitives. Area fill in courtyard bottom and area fill on courtyard bottom. I assume that has to do with the other one because I didn't do a fill or anything. This one. Yeah, alright. I'm just going to release anyway then. Let's try that again. Ignore those errors. Release anyway. See what happens. A solid strategy. Okay. So now, I should be able to place this part. But I think the edited version is only in my favorites. This one. Oh, I might have picked the wrong. Hold on. Come back. I want to make sure I place the correct footprint. This one. Okay. Now I can place it, and I need 2 of these. 1, 2. Okay. That's good. Alright, I need to add these to the bill of materials now. So, our ever-growing list of parts. What was our last U component? U4 for the Teensy 4.1. I don't see any other U's. So U5 and 6 will be these ones. Alright. Don't know this one just yet. And let me see if I can find this part in like DigiKey or something. Ha, I did. Oh, and it's in stock. What luck. Alright, part number. try not to bash Adafruit part numbers too much, even though I don't think they're very good. They are simple, I'll give them that. But I think in this case it's kind of a hindrance. Okay. So we'll name this U5 and U6. Okay, now we gotta figure out how to wire these up, and I think our pinout should have that we decided before. So anything that says Adafruit 2809, let's see, there's multiple, so there's a 0 and a 1. 0 will be U5, 1 should be U6. And the signal names. So we need to wires to it naming following those names. A1, A2, A3, and interrupt 2 I believe are going to be disconnected, but I'm going to read through this data sheet, or at least, it's not really a data sheet, but at least Adafruit's article on it and see what I need to do to connect up everything else. Okay, Adafruit 0. SDO, okay. Let's just get a bunch of wires out. Because all this will likely have to be connected. I'm not sure what this does. I'll run it out anyway, but I don't see that being used. Okay, SDO is MISO. Just do net labels on everything. All right, master in, slave out. So that's the data going back. So that's the data that our actual GeForce data is going to be coming back in on that line right there. So that's the first one. Adafruit 0, accelerometer 0 CS goes to the chip select. That's a mouthful. All right. Is there anything else? Really? Nothing? Is it just SDO and chip select? That's all I have listed in this datasheet, and I can't for the life of me imagine that, but I guess that kind of makes sense. So accelerometer, there should be a clock line if it's SPI. I've got to have something mislabeled in this spreadsheet. Okay, I do. I don't have something necessarily mislabeled. I'm just reading this badly. Oh, I found it. Never mind. Okay, so SDA is master out slave in, so that's how we talk to it. So Mosey is SDA. And then SCL is connects to the SCK line. Okay. Then let me double check the rest of it. So VN is probably 3 volts. 3 volts is also, what is the difference between those two, actually? Oh, you know what? I bet this contains, I remember reading about this. It has level shifting logic in it. So VN is probably whatever level that your communication is at, which is going to be 3 volts. And then this is the actual 3 volt line. So let me double check that in the spreadsheet or in the data sheet. Just be safe, but oh, okay, so 3V out. This is an output pin. We actually don't need this. Because we're not going to be powering anything off it. I wonder if it makes sense to connect that to anything. I don't think so. All right, let's just disconnect this whole wire. And then this is going to be 3v3. Obviously, this will be ground. Actually, I don't need to label that. Hold on. Let's just get our ground power port. Oops. There we go. Okay, and then the INT, what is that? So for SPI, we need SCL, SDA, SDO, and CS. INT is an interrupt output pin. So you can configure some sort of interrupt to fire when you... That's really cool, actually. Both of these, I2 and int, are interrupt output pins. I could see that being useful somewhere. I have a limited amount of I/O left on this board, though, so I don't want to just use them unnecessarily. But I see that that could be useful in the future, rather than possibly missing data. So I think I'm going to include that. I'm going to leave it blank for now, but I am going to include that when we do a run through again to decide what the remaining I/O should be. That'll be included. Why is this red? It is connected. Oh, it's probably not on the teensy. Okay, let's do the other one. Since we have to do two, and then we'll go ahead and wire up the teensy with everything as well. I can't wait to see this in the, oops, here, let's play as a PowerPoint. I can't wait to see this in the 3D view and everything. I'll do that once I get all these wired up with the teensy and everything. I'll export the changes and show the circuit board. Okay. As usual, if anybody has any ideas or suggestions, please let me know. Or questions. I like questions too. Oops. Otherwise, I'm just going to sit here and talk to myself the whole time. Alright, so this is 3v3. And then the rest are determined by the spreadsheet names we came up with. So CS is Accelerometer 1 CS. SDO is MISO 1. So I put these on different SPI interfaces. SPI can communicate to multiple things at once. Not at once. It can switch on the. You can put them on the same wires and then switch between which one you're communicating to, which is great. But accelerometers are constant stream of data, so I figured it was a good idea to put them on different networks, so that I could talk to both at the same time. That way I could get data faster. Because I'm not sure how fast I'm going to need to get it. All right, Mosey 1, it goes to the SDA. And then SCL is SCK1. Okay, and none of those exist either, so that explains a lot. All right, so now let's go over, save that, and then pull up the teensy schematic. And we got to add all that in here. We already have some of them, Mosey and Screen CS. All right, let's go down the list then. Pin 0 is Accelerometer 1 CS. I should just go ahead and add a bunch of wires here, because I have a feeling I'm going to be using most of this. I should double check the 3.3 volt output here if it can output a lot of current, because it looks like if I'm going to be powering the these accelerometers off it, I might need to double check that. I'd hate to be in a situation where there's not enough power coming out. Okay. Just going to go ahead and make lines for everything. We are very fast using up all the I/O. So, and according to the spreadsheet I have over here, I only have 5 pins that aren't spoken for yet. So this is going to be awesome. Okay, so pin 0 is accelerometer 1 CS. Probably need to move that out a little bit, actually. So we get some room there. Okay. All right, what's pin 1? That's MISO 1. All right, pin 12 is just MISO. This one. Oh, man. All right, I missed one. Mosey already exists, so I don't have to worry about that. All right, accelerometer 0 CS is on pin 36. Okay. I missed 26 and 27, I believe. Yep. 26 is Mosey 1. Uh, 27 is what? SCK1. All right, pins 30 and 31 are spoken for, but I don't think I'm doing anything with those yet. Yep. Okay, and then so that finishes that. I did accelerometer 0 CS. What's next? I think I've almost got them all. Or that might be all of them. Yep, okay, because the other things were already in there. So it looks good. So if we save this and go back here, yep, nothing is red anymore, so that's good. I just realized this is going to be throw an error when rendering. or when compiling because of all these unconnected lines. But let's try it anyway. Validate. Net so-and-so only has one pin. It's going to make me go through and fix that. Fine. I really do need to see what this looks like on the circuit board because I need to get an idea of our spacing. Because I know that we are definitely getting close to running out. All right, let's compile. No issues. Let's push the updates to the PCB. Validate everything. Unknown pins are weird. Execute. Everything executes just fine though. Yep. And there they are. All right, come here. Let's pull this out. Give it some space here. All right, all our components so far. Let's see how they compare to the others. Oh, that looks cool. And our little USB-C port. I still like seeing that there. It's such a cool model because we were able to download it rather than make our own. All right, that looks good. All the connectors and everything is still looking good. All right, I think that's done. Save that. And let's save the whole thing to the server. Just so everything's backed up. All right. What is next? I guess either we've done pretty much everything except the speaker and the motor. Motor's probably easier. So maybe we do that one next. I was thinking the other day about this motor too. There's a few things we gotta solve here. A, we have to get some connectors for it. So that's gonna be a little tricky. And then B, they use a lot. Motors use a lot of power, and I probably need to double check, see how much power this motor can use, like how much current it's going to be using. I don't know if we've got it. Like I don't know if we can supply enough. I know our batteries can. Our batteries can supply a ton, like 8 amps or something. But this voltage regulator is going to be struggling. It's already going to be maxed out with the lights on the blade mostly, so we might need to see if we can find something even better than this one. But I don't know on that yet. All right, let's check out our motor then. Maybe if it doesn't use too much, I can ignore it. I'm just worried because there's a few unknowns here. Like the TC can use a fair amount of current. The LCD screen is not too bad, I don't think. I don't know how much the accelerometers use. All right, let's see what we got here. This giant piece of work. I wonder if it says anywhere here. All right, let's go look at the data sheet. Sorry, I apologize. I'm tired. Rated voltage, 5 volt DC constant. 35 milliamps max. Okay. Under load 150 milliamps max. That's actually a lot better. Starting current 260. Oh wow, to fire it up. We might be in a spot where when this thing turns on, the lights get dim if they're on full bright. We might have to limit if the motor works based on a certain brightness of the lights. Interesting. I might pick up something else too. Alright, well, that seems fine. Just 2 wires, so pretty basic. Let me move these over. And then I think on my spreadsheet I've already decided how everything's going to be connected. We're going to connect everything through an H-bridge chip. So I need to figure out what that is. Like what the part number is. Oh, I guess it's here. The L293NE. And then I set this up for multiple motors actually. Just in case. All right. So here's our data sheet. This little chip is like $4 because it's notice the heat sink and ground requirements here. There's a strong possibility that this thing's going to get hot, especially pushing half an amp through it if it needs to. All right. There'll be an example in here somewhere. That's interesting. Okay. Parameter measurement. We're not doing anything like this. We only want it to go one way. Oh wow, this thing's supply up to 2 amps. That's why it needs those heat sinks. Jeez. Okay. Typical application. Inverted, yada yada. Looks like it has pull-ups on the enable lines. Oh, that's for a 2-phase motor driver. I think I just want something a little more basic, right? All right, well, there's a lot going on here. So let me just start by getting the part down. Close this. All right. So for our motor, we need to place a part. And chances are that this part does not exist, at least doesn't have a footprint. Let's go all parts. Oh, it does? Oh, but it's wrong. But the footprint is right. But the symbol is like something else, which is probably similar enough to be used, but I really don't like that. I'm going to edit it. Four, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. What is it? 4 and 5 are the heat sink. Yeah, so this is definitely something weird. All right, let's edit this. See what we can come up with here. I think this footprint is correct. I will double check real quick. But I'm willing to bet it is, because it's basically, it's a pretty standard size package. Real quick. Look at this awesomeness. In the recommended layout, these ground pins are all one big plane with vias going through them to spread that heat out into as much copper area as possible. That's fun. All right, good to know. And good to know on the capacitors as well. Where is the footprint? It might be in a different document. This is like a standard package, so okay. It looks like, yeah. The oh, wait. Technical documents. Click here. The page on the TI website will hopefully have it. Package PDIP NE. All right, well, there's a schematic of the package, but they still haven't given us a footprint. Let's see. TI-PDIP footprint. Let's see what we got here. Okay. Got a few option results here. Well, got nothing. I just get the same drawing again. Spacing Yeah, I'm just going to edit this real quick. And let's just check if the spacing is like reasonable. So that's on 0, 0. So what's this across at? 0.3 inches across. Yeah, that seems about right. And then the pitch is 0.1. Is that negative 100? Yeah, okay. This is correct. So I can just ignore this. No changes required there. All right, this definitely requires changes. Also, why did they name them backwards? Why 1, 2, 3, 4, 5, 7, 8 on that side and then... I'm just gonna let it go. All right. Here we go. All right, so I'm actually going to switch the numbering to... All right, so this is to enable. This is 1A, 1Y, ground, ground, 2Y, 2A, VCC2, then going up the other side, 3, 4 enable, 3A, 3Y, this is ground, ground, 4Y, 4A, and VCC1. I think VCC1 is the 5-volt dedicated line, and the VCC2 is whatever voltage you want the motor to run at. In our case, it will be also 5 volts. And then I totally forgot to check this. The logic levels, actually. So this is a 5-volt chip, but we're running it off the teensy, right? So, and the teensy is at 3.3 volts. I want to say I've checked this before. I'm sure I have, but I forgot. Output voltage, logic supply current, output supply. Somewhere in here is going to be an explanation of what on the enable lines, or on the input lines actually, what the thresholds are. High level input voltage, low level input voltage. So low level needs to be below 1.5 volts, high level is above 2.3 volts. Oh, well, that's easy. Okay. So yeah, we can control, so interestingly enough, we can control this off of a 3.3 volt line. Logic supply current required milliamps. Quite a lot. Oh, wow. Level, all outputs at high impedance. There could be a lot going on there. We might have to use buffers for this. Yeah. Just in case. And some pull down resistors maybe. Interesting. Okay. So there's still a lot going on here. I need to renumber all this. Let's just start with that. Nope. Four, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16. All right, cool. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That looks good. All right, so I think this part is done. Now it's just a question of how to wire it all up, and we can start on that because that's going to be quite complicated. But first, let's make sure this is good to go. Okay, and then we will place the part. Where is it? Really? It didn't... Can I edit this again? LTV847. I need to change that. So this is L293ME. Okay. L293NE. Okay. Save that. That should update that, hopefully. And save that to the server. Okay. Now let's try it. NE. Why does it say 6? Whatever. At least the naming is mostly fixed. All right, here's our chip. I don't remember how I'm supposed to connect all this up. Okay, so motor enable is pin 1. Motor 1 goes to pin 2. Motor 2 goes to pin 7. That's connected to the teensy. And then I guess the Y is the output. Okay, and then 5 volt goes into, I know for a fact 5 volt goes in both those. So we can do ground and 5 volt first. Actually, first let's line this up. And then draw our wires out. Okay, 5 volt on those, and then we need grounds. All right. So the rest of this, so these are not going to be used. I'm wondering if they need to be tied some way. The outputs probably don't, but the input may be tied to ground or something. I think the enable's active low. All right, so this is going to take some thought. Maybe not too much, actually. You probably want pull downs on the control lines. Is the enable line connected anywhere? Yes, I did connect. Okay, so I don't know if, I guess just to be safe, the enable line as well. Probably needs to be pulled down and then driven through a PFET. Probably from the 5 volt supply, now that I'm thinking through it. That would make the most sense. Okay. We've used a PFET before here. So let's find that. Those are NFETs. Let me look here. All right. P channel, revolt 4 amp, D2 pack. That seems intense. Q11, Q12. What do those mean? Those might not be the things we want. Where do we have put that? What were we working on? NeoPixels, maybe? Yeah. Yep. This part, the Q11 and so Q10, Q11. If I go here, where are those? Q11, Q10. Those are enormous. I don't need that. I need 60 milliamps at most. So I'm going to have to pick a different part. Dang it. All right, let's pick something else. All right, we want P channel, in stock, active, apply all, and then we really want like an SOT23 package. Let's just pick all the SOT23 packages. See what we get. 116 results. I have one that I've clicked on before. I must not have used it. Don't know why though. So I'm gonna need 1, 2, 3, probably. Let's see if I've searched one before. For whatever reason, I didn't pick this one. Probably because there was no model. All right, I think I want the SOT, the 23-3. A lot of great options. Let's see what we can come up with. Just trying to find something that's already been made. Nope. Just because, wow, Toshiba does a lot of this stuff. It'd help me a lot if I don't have to make the package myself. Okay, this one exists. Let's do that. They are in stock. Hang on, just gotta check through everything again. Huh. Show voltage. Interesting. Yeah, still some stuff I need to learn. I think this will work for now, but I might have to change something on the fly later. All right, let's place it. 1, 2, 3. Okay. Q12 through 14. All right, let's add that to the bill of materials. Oh, I guess I got to add this part too. So 7, and then Q12 through 14. All right. All right, real fast. Let's add this stuff in. All right, that's good. And then our little FET here. Part number. There it is. Doing good. All right. Now, how do we wire this up before? We did it on the NeoPixels, right? So power, this was data. So power on the bottom. Make sure, oh, they're not running the same way though. Out through pin 2, I believe. Okay. Yeah. And then into the device. Okay. So how are we going to do this? Probably just go way out, actually. All right, let's run control lines to all of them and power to all 3. And the control lines will need pull downs probably. In fact, let's just move everything over. There we go. All right, and then we need 5 volts. And then I'm actually going to turn the name off on all of these. Turn the comment off. All right. How's it going, Beth? We need this to be 5 volts. All right, and then I believe A is the input. If I check here, three, 1, 2, 7. Yeah, okay. So we need to run a wire from here to our enable. One from here to that input, and then one from here to the input down here. There we go. Good. Glad your Tuesday's going well. Okay, so now we need to name these. Oh, I might have messed up on this. We might need more than this. Aux 1. Did I pin out everything on this device? Nine and 10. Do I have something for pin 15? Because that would be epic if I did. No, I don't actually. Interesting. Oh, yeah, I do. Yep. Dang it. I thought I almost had it. Okay. We need to organize this a little better. or this is going to go nuts. Okay, give me a second. So let's take this, slide all this down here. All right, then I'm gonna delete this. I'm basically gonna redo it all. But I basically need like 3 more of these. Okay. Let's slide these up. Whoops, don't need a part, need wires. There's just so much going on here. But we'll get there in the end. I'm curious to see, especially here too, like how much space it's going to take up on this thing. When you consider all these circuit elements, because like these little pieces are probably about this size, but there's going to be a bunch more of them. There's going to be like 6 more, plus that chip. So yeah, this is going to be great. Okay, I think we confirmed from here the way this goes. Yep. So those are the lights. So power to the top. All right. I'm just going to run these across. And then run this up the middle. All right, and then this will be our 5-volt line. 5 volts. Okay, so now our outputs are going to run this way. Can't believe I decided to wire this whole thing up. That seems like a terrible idea. I guess I'm planning on doing connectors on this or something, or a header or something. I didn't even think about that. The outputs haven't been defined. Okay. All right, then in each of these, we need to go through and add these signals. Okay, so I guess I gotta come up with names for these. I could just name them based off their pins. 12VN, 1A, 2A, 3, 4 yen, 3A. I don't know if I should use a connector for this or what. I guess I would only need 8 pins on a connector. That might be the good solution right there. Okay. Not a wire. I need a net. One 2 yen, 1A, 2A, 3 4 yen, 3A, 4A. Okay. And then from there, I can name these things. Motor enable. This is motor 1. Motor 2. Aux enable, evidently. And then aux 1 and aux 2. All right, perfect. What else do I need? Oh, I need to add those to the teensy, and I also need over here. Oh, actually, I'm going to put them on these lines here to make it easier to understand. I need pull down resistors on everything. Yep. All right, so I'm going to go off of, I just use 10Ks. And because they don't need to be strong. Well, I don't know what the leakage current on this would be. It shouldn't be a lot. It would be a tiny amount. Hold on. These things always have a slight leakage current, so let's just figure out what that is. All right, gate source leakage current is typically 10 microamps. Doing a quick Ohm's law. Microamps are tiny, but let's just double check here. We just need to make sure that we can produce a bigger current than that. So, V equals IR 5 divided by 10,000 gives 500 microamps. So that'll be enough to drain it. All right, and I think I just realized that my spacing here doesn't really make this easy to do. Well, maybe it does. All right, so what 10K resistor have I used before? And then I need to add capacitors to the power lines, or to the VCC lines as well. I know I've used 10. Okay, here we go. Excuse me. I know I've used a 10K somewhere. And here, I think I found it. So let's look for this part. Our friend the Panasonic resistor. Just gonna drop one there, one there, one there, one there, one there, and one there. All right, and then I want to turn the name off on all of these. Oops. Okay. All right, then I need a ground. Probably right there and right there. And then wires. All right, and then these will all be connected to these enable lines, or control lines. And then I need to add that into my thing here. So through resistor 25. All right, that looks good. Now, you know, now that I'm thinking about it, since we're powering the chip off 5 volts, it might make sense to have a control line on these as well. I'll add it to my list of items to check on later. No, but I feel like I should check on that now. I'll look at that next time. I want to finish out this part. All right, so we need capacitors, and I saw some examples in here on this particular chip. Let's see. Here we go. Might need capacitors on the outputs as well, if we want them to stay stable. Here we go. Down here it recommends 0.1 microfarad on the 5 volt line and 1 microfarad on the power input. So I believe I have all of those, or both of those, available already. Yep. So 0.1 microfarad is this one. And then the other one, the 1 microfarad. Goes there. All right, so the 0.1 is C21. And the other one is C22. All right, let's flip that 90. Same with this one. There we go. And then, okay, that one's already connected accidentally. There we go. And that one will go there. All right, and then power port, we need a ground. Or I guess we could just connect directly to the grounds. Okay, so there's our capacitors in place. All right, so there still might be some stuff that needs to be done here. We also have to decide a connector for the whole thing as well. But I think this is a good start. And then so let me go ahead and, oh, we need to add this stuff to the teensy. I'm trying to wrap this up. I'm so tired right now for some reason that I really just need to take a break soon before I make a mistake. All right, so pin 37, 38, 39, 40, and 41. 7, 38, 39, 40, 41, and then one more, 14. Okay. And then I don't think we need a whole lot of space, so let's drop one there, one there, one there, one there, one there, and one there. All right, 37 is motor enable. .38 is motor 1. Motor 2. Aux enable. Aux 1. And aux 2. Wait. 41 is aux 1. I missed aux enable. Hang on. All right, there we go. So now I'm going to take this, compile everything, push it to the board, just so we can see it all there. No errors, good. Lots of changes to make. Okay, so much stuff has collision warnings. Hang on. There we go. And I'll just try my best to move everything out here. Man, it is going to be incredible to try and... Oops. To try and fit everything on this board. What are these? Collisions. Oh, just resistors that are in here, I think. No, what's this? Yeah. Our little FETs. So much going on here. Just try and drag everything out. I give up trying to put it all up here, but... Okay. Everything all spread out right there. I think I'm going to seriously have to think about how the heat sink on this is going to work. Because it's not going to be trivial with as much energy as this board's going to generate. All right, if we go to the 3D view here, we can look at everything. Oh, really? What is this? I might have to go in and change this model. Because that looks horrible. Alright, we're getting close though. We'll just... Next time I'll do some investigation on that, see if we can figure out if I need to add anything else. I was thinking about... I need a way to turn the chip on and off as well to power up that whole circuit controlled by the teensy. Otherwise, I think I run the risk of some serious drainage. Let me just check what the typical current usage is of this chip, of this H-bridge. Yeah, it uses 22 milliamps even at low usage, so we really want to make sure we only turn that on when we need to. Interesting. It says it can supply a lot of current, but the supply currents are showing levels that don't match that. Like, they're showing small levels. And I need to know, like... Huh. I'll have to examine this a little more, or I might have somebody who knows better what they're doing than I do teach me about this. If anybody has any tips, please message me. I'm just looking at, apologies for not having it on the screen, I'm looking at this H-bridge data sheet, just trying to figure out like how much current this is going to use while it's not being used, like if all the motors are off and, you know, whatnot. And I may just want to, that's why I want to have a way to turn this chip off, just in case. All right, well, thank you all for joining me tonight, and I'm going to take a break now. And we will continue more on this. We're getting so close to having this schematic done, and then when that's done, I'll take a look at this, and then I think I'm going to start doing the actual, like, partially start designing the hilt just to see, like, how big it really needs to be. And then from there, we can figure out how big the board will need to be and how much space we'll have. And we'll figure out a way to try and fit everything inside. All right, well, you all have a good night.